Okay, we're going to approximate the area bound between this line on the interval from 2 to 6 using a right Riemann sum with 4 rectangles of equal width, 8, 100, whoa, that's a little excessive, and then n rectangles of equal width. And then we're going to find the exact area. Actually, if you want to, you could jump all the way down here and find it because this is a line, and therefore we can simply use some of the strategies that we have used in the past, which would involve basically just finding the area from 2 to 6 of this trapezoid. We're not going to do that though. We're going to sort of build to something. So even though we could easily find this exact area using the area of a trapezoid, we are going to use 4, 8, 100, and then n. So we're going to make this a little more abstract. This lesson has a strong level of abstraction to it, okay? It's a little bit wacky, so hang tight. You may not have these graphs, you don't have these graphs, but I'm going to do this so you can have a visual for what's going on. So don't feel like you have to draw all this. In the process of making the video, I thought, well, let's just print some graphs. So 4 rectangles of equal width from 2 to 6. So let's draw, first of all, let's go from 2 to 6. This is going to be very rough because I don't want to just spend my time coloring. I don't know why not. So if I had 4 rectangles of equal width on an interval from 2 to 6, let's use a formula that we have dealt with a little bit in the past. First of all, my interval width is, well, 4, which is fairly obvious, and I have 4 rectangles. So just in case you forgot, this right here is b minus a divided by n, where a and b are the endpoints of the interval, n is the number of rectangles that we're dealing with. So in this case, I just get 1. So what that really means is each rectangle is 1 unit wide. So this is the rectangle width. This is the formula for it. You have seen it in a previous lesson. So using a right Riemann sum, and we will use different colors here. So we're going to go up over 1, and then there's this. Again, it's not going to be pretty. We'll switch colors. We're going to go up over 1, come down. Okay, already you can tell this is going to be an overestimate. And then we're going to switch colors again. We'll just make it look very Christmassy. We'll switch back and forth between green and red. And there's that one. And then there's this one. There we go. Oops, coloring outside the lines. Okay, so that's what we're dealing with. I'm going to set this up this way. We've done this before. So first of all, we have 1, and that seems kind of pointless, but I'm going to put it anyway. 1 f of, let's do our first rectangle, and I'm going to go from left to right, although I'm doing a right Riemann sum. I'm going to go from left to right, and my first rectangle was based on the width at 3, so 1f of 3 plus 1f of 4 plus 1f of 5 plus 1f of 6. The purpose of this lesson is to find some patterns, and all of these were multiplied by 1. This might seem very pointless to parenthesize them and put a 1 there, but there it is. And time we learned some stuff on the calculator, unless it is in a previous video. I filmed that video. I'm trying to remember if I put it in that video or not. So here we go. Y equals, we're going to type that function, so 0.5x plus 6. Whoa, plus 4, sorry. Looking in the wrong place. There we go, there's our function. And I believe I did do this. So we're gonna go to second and list. Go to math. We want the sum of something. And we want the sum of what? We want the sum of a sequence of numbers. So second and list, we're going to go over to ops. First of all, math took us to sum. Now ops takes us to sequence. It's always number 5. And our expression is y1. Our variable is x. It starts at 3. It ends at 6, and we step up by 1 every time, and we're going to paste that. There is one thing I accidentally left off. It's not important. I am going to go back and put it in. It's not important this time. It will be later. Well, first of all, there's that. What I did leave off was this 1 in the front. So 1 times all that. Obviously, it's 1, so it doesn't really matter. So what we're doing is adding together 3 plus 4 plus 5 plus 6. Let me rephrase that. We're adding together f of 3 plus f of 4 plus f of 5 plus f of 6. I press enter, and I get 25. So the right Riemann sum is 25. Okay, this is going to start getting a little bit old because the patterns are going to become a little more obvious. So 8 rectangles of equal width. So same problem, different number of rectangles. So how many rectangles? 8. How wide is each rectangle? You probably already know it, but it's basically, well, b minus a over n, which is 6 minus 2 over 8, which is 1/2. So my rectangle width is 1/2. So as I do this next one, it's going to be 1/2 times. Okay. Now, I would love to just list them all, and I will. This is going to get a little excessive for this one, and I'm definitely not going to do it for the next one. But there's patterns here. If I was to, or if I were to, using proper grammar, if I were to draw 8 rectangles, they would be, and bear with me as I draw them, they would be here, here, here. You can see where this is going. Here, I do want to finish this process because you're going to get a visual for what's really happening here. Here, here. Sorry for all the clicking that you're hearing. Switching colors on my pen. Here, and here. Okay, so those 8 rectangles, again, are going to give us an overestimate, but let's compare. The overestimate of 4 rectangles versus the overestimate of 8 rectangles. Ooh, we're getting a better actual approximation of, almost said approximation, that's not right. We're getting a better approximation of the actual area bound between this line and the x-axis, which is a trapezoid. We're getting a much better approximation by using more rectangles. Just a little more work, but we're getting a better approximation. So there it is. And when we drew our rectangles, starting at the right, we went all the way to 6. But on the left side, we never had a rectangle that was based on f of 2. The closest we got was, watch it, watch it, watch it, 1/2 away from 2, okay? So our very first, I say first, I drew it last, but the leftmost rectangle of a right Riemann sum doesn't go all the way to the left. It goes this far away from the left. So it's based on, boink, that right there, that height, which is not 2, but 2.5. Or this one, which was also a right Riemann sum, did not go all the way to the left. Now, eventually we drew it all the way to the left, but none of the rectangles were based on f of 2. They were based on f of 6, 5, 4, 3. That was it. So it was 2 plus 1, or 2 plus 1/2. So when we get to the next one, I'm not going to draw all 100, clearly, but my leftmost rectangle is going to be 2 plus the width of the rectangle, which is going to be very, very thin because it's 100 rectangles, okay? So we're noticing patterns. That's the point of what's happening right here. Our rightmost rectangle was f of 6. The one beside it was 5.5, f of 5.5, f of 5, f of 4.5. Again, clearly I can list them all here, not going to happen here. F of 4, f of 3.5, f of 3, and you're like, oh, we're done. No, we're not. No, we're not. We got to get this far away from 2. F of 2.5. Oh no, you can barely read what it says. That right there says 2.5, just so you know. Terrible handwriting. Sorry about that. And we're going to find out what that is. So let's review the calculator steps again. Here we go. I'm going to type all this in. I'm racking my brain right now trying to remember if I've shown this in a previous lesson or not, in a previous video, because I recorded the other ones weeks ago that lead to this one. Okay, 0.5. 0.5 because, well, 1/2. I want to add a bunch of stuff together. That is a sum, and I can do that with the list option, so second and list. I'm going to go over to math, and I want to sum a bunch of stuff together. I want to add things together. So second and list. We're going to go over to ops, and we're going to add together a sequence of number. We are summing a sequence. A sequence is a list of numbers. Our expression is indeed y1. It's been stored in there. If you wanted to, you could actually, you don't have to do this, you could type the function itself. Don't have to. The variable is x. This one doesn't start at 3, it starts at 2.5, sloppily written. And it ends at 6, and it doesn't step up by 1, it steps up by 1/2. And we paste it. Close parentheses, it works if you don't, but that's okay. 24.5, ooh. Okay, so the actual area here, which we have not yet calculated, is, I'm gonna say that it's less than 24, or less than 24.5. And therefore we're getting closer the more rectangles we use. So let's use 100 rectangles. So here we go. Let's do this next one. B minus A over N, that would be 6 minus 2 over 100. That is 4 over 100, and that is 1/25. Whoa, okay, just for decimal sake, let's go 0.04. All right, not gonna list them all, but we've noticed enough patterns to where we can start writing some things down. So 0.04 or 1/25, f of, okay, not 2. Not 2 at all. How far away from 2 is it? Well, I'm glad you asked. If I could find my other graph, I'd show you. I'm throwing ink pens everywhere. All right, 2, and then 1/100th over. Because if I drew all 100, not gonna do it, I'd have 6, and then 6 minus 1/25, minus 1/25, minus 1/25, and I would do that. It'd be 100 of them, and I would end with my last one being right up on that 2, 1/25th away, 0.04 away. So it's 2 and then 1/25th, which is 2.04, and then f of, okay, 2.08. Whoa, where'd that come from? I'm adding 0.04 every time. And then f of 2.12, I'm adding 0.04. Now, this is gonna get really old really fast. So we just put a few dots in between a couple plus signs showing that the pattern continues, and we're gonna go ahead and end it with the last 2. The very last one is f of 6. The one before that is 1/25th away from that, which is 5.96. Okay, we're gonna type this one in the calculator. All 100 terms, I'm kidding, we're not. We're gonna use our little shortcuts here. Here we go. We have to put the 0.04 in this one, 0.04. Second and list, we're gonna go over to math and then sum. The sum of what? Well, the sum of a sequence. A sequence is going to be found under the ops menu. The sequence can be generated with this. That is the expression we are using to generate the sequence. Our variable is x. We do not start at 2.5. We start at 2.04, not 204. We end at 6, and we step up each time by 0.04. We'll paste that in there. Parenthesis for good measure, because it technically closes the other parenthesis from the sum. We're going to get a number ridiculously close to the real answer, and it's going to be an even better estimate. So before I press enter, keep in mind that the more rectangles you have, the better the approximation. It's a lot of error right there. That's less error. If I drew 100 of them, there'd be even less error, and there it is, 24.04. We probably know the final answer by this point, like the real answer, the actual answer. Okay, we're going to use n rectangles of equal width. Now things get crazy, so hang with me. Well, let's come over here and let's find how wide each interval is. Things get really abstract here. We've spent the first 3 examples building some patterns and understanding. Now things get ridiculous. So b minus a over n, why do I write it every time? Just so I don't want to ever forget it. 6 minus 2 over n, which is 4 over n. How wide is each rectangle? 4 over n. Okay, cool. Well, that's not a number. That's okay. We'll deal with it. So n rectangles of equal width. So we are going to have 4 over n. All right. Our first rectangle that we draw with n rectangles is going to be, wait for it. It's going to be 2, and then this much more. We've done that in every problem, whether we realized it or not. It was 2 plus 0.04, or 2 plus a half, or 2 plus 1. Well, it's 2 plus 4 over n plus f of 2 plus, okay, we're going to have, here's 1 4 over n. Now we're going to have another 4 over n. And then we're going to have a third 4 over n. We keep adding another 4 over n every time. And we're going to do that until we get all the way, whoops, getting carried away there with my plus signs. I need some dots in the middle. We're going to do that all the way to the end. And the very last one is 6. Okay? So what is this answer? Well, good luck typing that in the calculator, because now we're not just dealing with the variable of x that's implied here. We're also dealing with an n. So we don't have an answer. This is our answer. However, things are about to get a little bit ridiculous. So work with me here. I keep saying work with me here. We're building to something very abstract. Here goes. Here's a lesson within a lesson, and I'm going to use the back of my graph for just a second. So if you want to hold this thought, I'm just going to make up something totally unplanned. Here goes. Dun, 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 dun. Let's use k. K equals 1 to 7 of 2k. Okay, what in the world does that mean? First of all, this is the Greek letter sigma. It's an uppercase sigma, and it means summation. So I'm going to be adding a lot of stuff together. Calculators will do this. There's tricks to it, though. So what it really means is I'm going to plug in 1, 2, 3, 4, 5, 6, and 7 into this and add them all together. So I'm going to have 2 times 1 plus, 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. This gets old really quick, doesn't it? 2 times 6 and 2 times 7. And I'm going to get an answer. And my final answer is 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14, which is 16 times 3 and a half. 16, which is 56. There we go. So I wanted to show you what's about to happen on our paper. It looks ridiculous. If you look ahead at some of the things that are given to you, you're like, whoa, what in the world is this? Yeah, don't panic. Don't panic, okay? So if I added all these together, I'd get 56. That's what this represents. It means add everything. Plug in a 1, plug in a 2, plug in a 3, plug in a 4, plug in a 5, plug in a 6, all the way up to 7. So let's do that. This expression is the sum starting at 1 and ending at, well, how many rectangles do we have? N. Okay, all of a sudden, we've just had an explosion of variables here, but we're starting at 1, we're ending at N. Okay, what are we doing? We are basically going to take the function and then 2 plus a little bit more, and we're going to count up each time. We're counting up 1, 2, 3, 4 until we have n of these things. Because once we get to the nth one, do I have post-it notes? I do not, no. Okay, let me show you what happens right here at f of 6. I really have f of 2 plus, 2 plus 1 of these. 2 of these. 2 of what? 2 of the width, 1 of the width, 2 of the width, 3 of the width, 4 of the width, 5 of the width, 6. How many do we have? We have n of them. We have n of these. That gives me f of 2 plus 4, and that's where the 6 comes from anyway, okay? So what we're going to do is just count up 1 of them, 2 of them, 3 of them, 4 of them, until we get to n. This is our stopping place, just like 7 was our stopping place here. And we're going to have k 4 over n. Okay? But because of this 4 over n that would be multiplied by all of them if we distributed, we'll still have 4 over n out here. Now, I know you're like, well, we can multiply. No, no, don't. This is f of this times that. Okay? It's going to get crazy. Now we're going to find the exact area. That's the not crazy part. This is the part where we take a breath and we were like, oh, I got this. Oh, getting kind of crazy. Whoa, noticing some patterns. Oh my goodness, my math just exploded, and back to basic geometry. Okay, find the exact area. We will draw this one. So let's just draw it. I know I have graphs I could deal with, but I'm not. So this is what it is. And then 1, 2, 3, 4, 5, 6. And so 2 to 6. There it is. I'm going to find that area right there. This is just going to be basic area. I know, again, taking a breather from this ridiculousness that just exploded. 1/2 height, base 1 plus base 2, because we're dealing with the trapezoid. 1/2. The height of my trapezoid is 4. That's it. If I turn it sideways, it would truly be height, like vertical height. 4. And then base 1, which I don't know what that is, but that would be f of 2. And then f of 6 is my other base. So ever how high that is, So 2, and then if I plugged in a 2 into the original function, I'd get a 5. I'm glancing at the top of the paper as I say that. I just plugged in a 2. Let's also plug in a 6. That would give me a 7. Is it a 7? It is indeed a 7. Okay, 5 plus 7. And so I have 2 times 5 plus 7. That's going to give me 2 times 12, which is 24, which I kind of had a guess on that anyway. So, oh, excuse me. Excuse me very much. So sorry. 24 is the actual area. We sort of were getting there by picking larger and larger values of n, more and more rectangles. So the more rectangles you have, we've said this, the more accurate you are, and therefore the ideal is to have, wait for it, an infinite number of rectangles. Well, you can't put infinity up here. You have to approach infinity. So we have f of a. What's a? A, huh? That's a. That's your starting point. This is a right Riemann sum, by the way. We start there, plus k. K is what we're counting every time. I go up 1, 2, 3, 4, 5, and I don't stop until I get to n, which really means I never stop because it's infinity, right? And then delta x, what's delta x? This is that. This is the width of each rectangle, which really means that if I have an infinite number of rectangles, each rectangle is infinitely skinny. It approaches a width of 0. So this is more theoretical than actually, plugging things in. This was hands-on. You could draw it, but you don't want to. You don't even know what you're drawing. And now we have like an infinite number of rectangles. This is where we step into the realm of taking patterns and extrapolating on them to get a formula to do what? What are we doing with our formula? I'm glad you asked. We are going to be figuring out the area right there. We're figuring out the area, and that is what this represents. We are going to use this notation a lot. So if you stare at that for just a minute and you're like, oh my goodness, I have no idea what I'm even looking at. This is the most ridiculous thing ever. What is this? Do not panic. That notation is going to happen a tremendous amount as we move forward. So again, you have just been introduced to a lot of new notation with the summation and this funky thing right here. And what is that? It's all going to come together. In the meantime, here's what you need to know. You have learned how to do left and right Riemann sums. We did right Riemann sums with an infinite number of rectangles to figure it out. We haven't quite done it, but an infinite number of rectangles will give us the exact area, which is what this truly is.